So we have both the speakers, Professor Hendrik and Professor Peter Barker. So, and we have also invited Professor T.P. Singh because he was also involved in a lot of work that was displayed. So we will start with the questions, and we'll start with Surajit Saha first. May I request Surajit Saha to please come to the mic and nearest mic. Yeah.
Hello, sir. My question is, in any macroscopic classical system, there are many atoms. And within the atom, the electrons and other subatomic systems are in a quantum state, which we conventionally call superposition state. Now, if this classical interacted with a classical object, or according to collapse model, it can collapse spontaneously. So, there must be a minimum collapse volume within which collapse does not occur. Then, within a macroscopic classical object, superposition is still alive. Now, the question is, the large mass limit and the minimum collapse volume are two different aspects in the investigation process of quantum to classical transition. Are there is any relation between these two type of aspects? Is there any way to determine experimentally the minimum collapse volume?
So who should answer?
And also, now...
Oh, what? That was a long question already.
Now, the related. Now, as we know, there are non-locality even within a single particle wave function. My question is, to determine the minimum collapse volume, does some kind of spatial distribution of the single particle non-locality plays any role?
Okay, different types of answers to your question. So the first is, Peter showed this in his talk, when you think about these experiments by Marcus Arndt, where you have these complex molecules and you generate a superposition state. What you find is that for some reason, all the internal states, so that's what you mentioned, electrons, phonons, excitations, conformation changes, dipole moments, and so on, they don't affect the center of mass motion if they're not coupled, and that means they're not affecting your superposition state. So in all of this, the important parameter is the center of mass motion degree of freedom, right? And if the other degrees of freedom are not coupling, then they don't decohere the system or they don't collapse the system. That's one point. In the CSL models, there is a certain parameter range which is assumed fully ad hoc, yeah, that is just for convenience, and that's on the level of nucleons, so protons and neutrons. That's like the size you look at, and when you count how many particles contribute to the total mass, then you count how many protons and neutrons you have. And depending on the details of the model, you come up with a certain, as you call it, minimum volume and, let's say, minimum mass where the collapse should happen. Yeah? That depends on the very details of the model. And you could likely also write it down in a different way, but historically that was done on the level of nucleons. Yeah. I don't know if it answers all your questions, but I hope some. Do you want to add?
Yeah, can you hear me? Just to add to what Hendrik said, just make a very simple model, which is the underlying principle of collapse models. You start, let's say, with a nucleon, a proton or a neutron, and consider a position superposition of two positions of the proton, let's say, and now make a hypothesis. This is the principle of spontaneous collapse, that this superposition will collapse on its own once on an average in a very long time period t, let's say of the order of the age of the universe, 10 to the 17 seconds. This is a proposal. This number is a proposal. Now if you consider an entangled state of two protons, yeah, proton 1 here into proton 2 here plus proton 1 there into proton 2 there, this state will now spontaneously collapse twice as fast, because if the first proton collapses, it will take the second one with it and vice versa. Now scale it up. If you have n nucleons entangling with each other, the superposition lifetime becomes T by N. You agree, no?
Yes.
If T is 10 to the 17 seconds and N is 10 to the 23, like in a macroscopic object, the superposition lifetime has become a microsecond. This is the beauty of large numbers. Yeah? So we don't see macroscopic superpositions according to collapse models because the superposition is collapsing extremely rapidly just because there are so many particles in the system. So in this simple picture, the scaling is with the number of entangled particles in the macroscopic object. That's the simplest picture you can make. Does this make sense? Yeah? Yeah? Okay.
Okay, so the next person is Shayan Chakravarti. Can you please?
Hello. Both talks are really amazing. So I have a question to Professor Barker. Like in the 11th slide, so exactly. Can you please explain again? I did not catch up with the grating in the middle, which is showed in the green. Can you explain that grating? Like how is it different from the like G1 and G3, that G2?
Yeah. Oh no, it's fine. Yeah, no, that's quite clear, which is the green grating. So the difference is that that is a grating made of light. So the modulation to the wave function, or basically the creation of the superposition, is due to the optical forces, so actual dipole forces. And the reason why you need that is that these things are so large that they would actually, I mean, it's a very clean interaction in terms of the diffraction process compared to if I had a material grating in the system, because your molecules would get stuck onto that system. So for such large systems, you need to have a very pure grating function, and that can be provided by the optical forces, the optical dipole forces, but also absorption as well. So there's a little bit of absorption that occurs. So, you know, for these larger particles, and as Hendrik showed, like when you get even larger, you know, if you have something on the order of 100 nanometers, then you need to use these optical dipole forces from an interference pattern, essentially.
Okay, so one last question, like here in one of your slides you shared that the spread of the wave packet, that is like kind of 7 nanometer. So like I have a curiosity, like how to measure the spread of a specific wave packet in an experimental setup?
So I could show you that, but essentially, I mean, we can measure position actually down to sort of picometer type resolution, and that depends on the time scale. But using sort of a homodyne techniques, we can quite easily measure that sort of positional accuracy. But of course, the problem comes that if you want to do some interferometry, you need to, and this is what Hendrik spoke about, is that you need to have, you know, your wave packet that is basically can be modulated by these optical forces or by some method. And so that's why Hendrik was talking about the fact that you need to basically, this is why you would like to go to space, to expand that wave packet to a point where you can do something with it. So, you know, if you need to wait a long time for that wave packet evolution in standard methods, then, you know, you need to go to space, basically. What I was talking about actually is a way to accelerate that expansion, and Hendrik also mentioned that in a separate way. And that, I think, to do anything on Earth with the systems that we currently have, that is what you need to do.
Okay.
Okay, so next, Dibojyoti.
Okay, first of all, thank you. Thank you, everyone sitting there, Professor Ulbricht, Professor Barker, and Professor TP Singh. It's an honor to be able to interact with you. Big fan. So, I'm Dibojyoti Mek. I am a final year BSMA student here at ISO Kolkata. So, I have been studying the CSL model of wave function collapse applied to harmonic oscillator in 1D. So I have the questions which is pertaining to the CSL slide. Sir, can you please go to that slide?
Which your CSL equation.
In this one?
No.
The other one?
If it's equation, it's for you. Yeah.
Oh, I'm going in the... Okay. This one?
No. Yes, this one. Okay, so while trying to understand the anatomy of the equation, like I understood, like there is a nonlinear term, there is a stochastic term, and there is a unitary term. So, there are certain things which are unclear to me. For example, the noise correlation function. Is it needed to be spatial or spatial temporal? Another question is as we can see, like in many other papers, there is the use of mass density operator and as well as position operator. So, from a theoretical and experimental point of view, when do we expect to use the mass density operator and when do you expect to use position operator? These are the questions. And I have one more question that I will ask after this. So.
Okay. I think it's a question for TP, but I have like a very brief answer, and that is there are different types of models. So this is the one which is, in position space and where you use this mass operator and where you have the correlation as it's written down there, but you have like different models where you also look at the other correlation functions, and I hand over to you.
For indistinguishable particles, you would like to have this, yeah. So, as Hendrik said, there is no theory of collapse models which will tell you what function to choose, yeah. So, go look at it. The minimum philosophy of writing down such an equation is that, see, you want collapse to happen. You want collapse to be less likely for small systems, very likely for large systems, and it should produce the Born probability rule and randomness of outcomes. So, and you don't want faster than light signaling. These constraints, no signaling and getting the Born rule out. The second thing requires that even if you add a stochastic nonlinearity, the equation should be norm preserving. So if you want no signaling and norm preservation and a stochastic modification of the Schrodinger equation, you will more or less land at an equation with this structure root gamma that is the nonlinear and stochastic term, but it should be balanced by one more term to get norm preservation. But other than that, which operator to use, which localization function g of x to use, you have choices. And you have a choice on the noise also. So now go ahead, please. What more, you were saying something.
Okay, another thing is what differences we expect to see for a single particle and a multi-particle system when the CSL model is being applied.
You want to say something, Hendrik? Yeah, so basically if you look at this gamma, this root gamma, that this collapse strength is a function, physically speaking, of the total number of particles in the system. So if you have a single particle, collapse will be extremely rare. And if you have an entangled state of, like I just said, of many, many particles, collapse will be very frequent. So one particle versus many particles, the rate of collapse will, is that what you are asking? Is it okay, Hendrik? Yeah, yeah.
So there is a follow-up here. Yeah. Speak a little louder. Shout.
Thank you. Yeah, I have a follow-up question to what he asked, so which is that how do these models actually allow quantum statistical effects in very massive objects like neutron stars?
You're a theorist.
Before going to neutron stars, you could also ask about Bose-Einstein condensates. So, is this okay?
Yeah.
So this is your question, macroscopic quantum systems, how are they consistent with collapse models? Is that your question? Yeah, very good question. So this keeps coming up. What causes very frequent collapse in a macroscopic system is having a large number of entangled states. We understand entanglement. If you take a BEC, it is typically not having so much entanglement. You might entangle 100 or 1,000. I don't know what's the record today. But you certainly don't entangle 10 to the 23 particles in a BEC. These are what you call product states of one particle states. You get what I'm saying? The collapse rate for such states would be typically like that for a single particle. Entanglement is important. It's not enough to have many, many particles. So superconductor or a quantum effect in a neutron star. So what we need to make is a BEC with an entanglement of 10 to the 9 particles. Then the collapse model will say you can't form such a BEC. That would be correct, no? Yes. Yeah, so okay, so can we do such an experiment? Very tough. Yeah.
Given the fact that the wave function has to be antisymmetric.
No, can we, one second, can we come back to that?
Sure, okay.
Yeah, because we have 16 questions and we should give opportunities to everybody. So next is Rajak Leskar. Yeah.
Okay, myself Rajak Lashkar. I mainly work on a multi-level system interacting with some laser field, more than one laser field. So it gives a electromagnetically induced transparency phenomenon. So using EIT, electromagnetic induced transparency, quantum sensors can be designed, where the electric field, the phase of the electric field can be changed. This is called Faraday rotation, and from that, any kind of magnetic field can be easily sensed by the spectroscopy in a probe absorption spectra. So I have a question that if that EIT can be used to sense gravity or anything else, because the spectrum of EIT is very sensitive to any kind of changes in the control field or any kind of environment effect can be easily be seen in the spectroscopy, in the probe absorption spectrum. So is there any way to detect or chance to sense the gravity using EIT setup? Is there any way?
I'm not sure. I mean, how you mean in terms of the systems coupling an atomic system to these massive particles, or did you have anything in mind? I mean, I can't immediately think of how you might do that. Can you?
I can also deflect a little bit on your question. I think you would need to think how you couple it to like a big mass, right? So you have a very sensitive sensor, but it is a transition, I guess, in a crystal or something, and that's sensitive to magnetic field. So if you can use the system and you can turn it into like a mass-dependent system, then I think you can probe gravity. What is maybe interesting, so that would be not necessarily gravity, but if you think of these tests of collapse models, so there you look for a noise, and you can maybe also think of spectroscopic or these, IT systems where you have very precise measurements of something, and there's like a noise coupling into your detection. So we looked at hydrogen spectroscopy, which is like one of the most precise, 1s, 2s, or something like that transition, which is probed. So Ted Henge has done these experiments, and they're like, you can measure fine structure constant, and it's like amazingly precise. Yeah, is really outstanding. So now the question is, in these systems, would you actually pick up some sort of noise which is predicted by these models that could include some gravity-related models? Yeah? And the answer is no. Yeah, it's too small. It's way too small by 10, 20 orders of magnitude. to be seen in these systems. And the reason is that the mass of these systems, so in a hydrogen atom, is too small. So it does not, basically, is not affected by these mass-dependent models. So that would be my answer. But, you know, I don't want to discourage your drive. And if you find a clever way to couple...
Because the full width half maximum of the spectrum is very sensitive to any kind of noise.
Yes. Yeah.
So if I intake those noises in Lindbergh superoperator term, then that can be effect on the spectrum, EIT spectrum, actually in Doppler broadened spectrum. That will be much more sensitive to those noises.
I understand, and I mean they're you know, different types of very sensitive systems which we use for metrology and precision experiments. Yes. And of course, if you after these kind of, you know, fundamental or foundational effects, then it's a very good idea to think about those systems and how you can use them to probe into this. And that's what we also did with collapse models. So like when we looked in you know, gravitational wave detectors or this germanium X-ray emission. Yeah, so that were existing experiments. People had done this already, and we retrospectively looked into them and basically worked out what kind of bounds they would give. So, you know, I think you need one good idea to connect your, you know, very, very sensitive sensor to these kind of models and ideas. Yeah.
Okay, so next is...
Oh, hang on, I'll just add to that. So actually now that I have a bit of time to think, so I briefly touched on this, so that, you know, I talked about this Ramsey experiment where, you know, using NV centers, and I guess, I don't know, presumably you can have EIT in that system as well, with that embedded system. So, you know, I think that that's possible. But actually what I didn't really talk about is that, so, you know, there are issues with NV centers in that they're not as clean as the atomic systems that we were talking about last night that you were looking at. Yes. And the idea here is that instead of using NV is to essentially associate, using again these optical potentials, associate an atom, so trapping an atom next to these much larger massive systems that would be sensitive to gravity. And then I guess, you know, in that case, I mean, certainly already in that system, you need to use optical fields to initiate or to sort of prepare, you know, for example, if you want to do a Ramsey type experiment, to prepare it in these hyperfine states to do this protocol. But, you know, you could also think of definitely, you know, because I'm talking about associating cesium with these massive objects, you could do, you know, very nice EIT protocols with that. What exactly you would do, I'm not quite sure, but you're right, you know, you have these very sensitive, very narrow, you know, frequency resolution, so it may be possible.
Right. So next
now I also got another idea. Yeah. Maybe, I mean, what Peter explained is like exactly right. So you have these narrow transitions and these very precise spectroscopy things, but if you couple them to like a large system, if they're not isolated anymore, then they typically quench, right? So you lose basically this narrow line width property, which is like the key to be precise in your measurement. So a great example is NV center. Yeah? That is like a present of nature. It has this isolated nitrogen vacancy, which gives you a narrow transition in the bulk. Yeah, so it's coupled to like a big massive system, but still you have like a very precise transition which you can probe. And you know, Peter's idea is like the proposal they had with the Paul trap. That's another, you know, very, very cool way to couple a narrow transition system to a big mass, to the center of mass motion of a big mass. If you can do this successfully, that would solve many, you know, problems that you could answer many questions. Yeah, that is like one of these big challenges, I think, in you know, experimental physics, is to find systems where you have this, where you have high precision and large mass at the same time. Yeah?
Thanks. Okay. So next is Archana Banner. Yeah. So.
Hello. Thank you for the nice talk. My name is Archana Barwad from ISER Mohali. So my question is a little basic, not very fancy. So both of you started with microscopicity, right? And then you related that microscopicity with the quantumness of the system. And you said we can talk about size, mass, and number of degrees of freedom when talking about microscopicity. And the point was that how long the system can stay quantum as the system becomes more and more macro. So my question is that what exactly is the difference between size, mass, and let's say number of degrees of freedom when we are talking about this microscopicity? And because on a surface level, they seem related that if a system is more massive, then it may have, because it's composed of many fundamental particles and it has more number of degrees of freedom. And how does that, like increasing mass causes decoherence or transition to classical? So that is first question.
So I think, I mean, it's not a simple question because I think there's many ways to look at that. And, you know, I presented this one model and there are many different ways of looking at, you know, macroscopicity, essentially, because, you know, as I mentioned, you know, that you can have a large mass in a superposition, but a small actual, you know, in a cat state, a small separation. But, you know, you can also have the opposite where you can have single atoms that are in a ½ meter superposition. So, you know, I think it is difficult to make that. But I guess the other thing is, you know, that's, I guess as an experimentalist, it's for us to look for systems and combination of systems, you know, where we can generate, you know, complex quantum states. And it's very much, you know, very much looking through and understanding these systems and engineering them. And that's actually when you start moving away from atomic systems and you can start engineering them, you can start building, you know, particles with particular properties or you know, or squids, you know, things like this, you can actually start controlling things. And so, you know, you have the ability then to actually engineer what you want so that it has, you know, the properties that you require. So I think, yeah, I think that there's no simple answer to that. It's basically, you know, understanding this technology and developing them to the point where you can do these experiments.
Yeah, so maybe from my side, I forgot to mention this in the talk, but there's like an interesting link. So when you think about this macroscopicity value, like the one Peter presented from Ulbricht and Hornberger, the intuitive idea is this, that you go for a system where you have large mass, large size, and for a long time, superposition, and you map this on an interferometry situation. So basically, you do like meta wave interferometry, like atom interferometry, and you tune these parameters, and then you compare what it is. And all the experiments which you want to measure with this macroscopicity measure, you somehow map onto this interferometry. And this is quite involved. So if you have a look at the paper, it is not easy to understand. And I think until today, whenever someone wants to have this macroscopicity number, they have to talk to Stefan and Klaus, because they're the only ones who know to calculate it properly. Anyway, what is interesting is that I think you can show, I mean, that collapse models, so CSL is actually formally equivalent to the macroscopicity measure. So that means what I have presented as like, you know, this exclusion plot with these parameters, that is for all practical purposes a measure of macroscopic. So when I basically want to decide, is that system, you know, a macroscopic quantum system, then I compare it how it can basically test collapse models. Yeah? And in the exclusion plot, I do exactly this. I take very different physical systems. So there's X-ray emission in germanium. There's like a mechanical oscillator in LIGO. There is like an atom in an interferometer. There's a molecule in an interferometer, and all of these systems, and they can be mapped into the same exclusion plot because I have the CSL model to compare them. So for me, that's actually the most important function of the CSL model, that I can define what is macroscopic quantumness. Yeah? That's my definition. Yeah.
All right, thanks. Can I ask one more question?
Very quick.
Okay, so I just want to know that you are talking about massive particles, and then as the system becomes more massive, so the effects of gravity become more prominent. But when we say something is massive, we are talking about in a very relative sense, that let's say this spike is massive than a proton. So can I not say that electron, I mean, it is a particle, it has a mass, so maybe my experiment is not as sensitive and delicate to detect the gravitational effect of the electron? So that is my question. So can I say that or not?
So what exactly was the question?
that can I talk about gravitational effects on an electron, because it is a particle and it also has a mass. So I can say that maybe my experiment is not as delicate and sensitive to detect the gravitational effects on an electron.
Yes.
Okay, so.
I mean, that is correct. But did you want to say something?
Yeah, very much so. Yeah. It is the exact same description with like the caveat that, of course, it's not a very sensitive system for gravity because the mass is so small, right? So you would have a very small macroscopicity value, or it would test a CSL type model only very weakly because the mass is not strong. But of course, you can treat it in exactly the same way. Yeah, that is indeed what you would do to compare it to a nanoparticle in a superposition. Yeah. With an electron, you would also have the difficulty that it has a charge, and then all the charge-related effects would be much, much stronger than the gravity ones.
Okay.
It's also interesting that this actually worked by Bob Wald and others who have looked now with the interest in looking at this gravitational entanglement, what would actually happen in electromagnetism? Could you have the same thing? And they find interesting things also in electromagnetism without going into detail. So you can see it there. And I think that is quite interesting because you can compare electromagnetism. We understand much better. We know QED and we know what the photon is and so on, with maybe still some mysteries, but broadly there's like a theory to describe this. For gravity, we don't have that. And we can look for differences and we can see how they maybe come out if we compare, for instance, what happens to a charged particle in these kind of cases compared to a neutral one. Also historically, now I start to talk too much, but historically it's interesting because when Schrödinger came up with the equation, he wanted to calculate the model, the hydrogen atom. And that is an electron in a central symmetric potential, as we know. And he actually treated in the very initial state, he treated basically the wave function as a real object, and he gave it a mass and so on. And if you do this calculation, you get the completely wrong spectra, and you cannot basically get the proper result for the hydrogen atom. And that they knew already experimentally at the time what should come out, and then it was like in some steps to come up with the right idea how to do the calculation. But if you do the naive approach with like an electron and you treat it in the Schrödinger equation, then you get like the wrong results. Yeah? So interesting things are there. Certainly.
Okay, thank you very much.
Next is Saswato Sen.
Hi, thank you very much for the nice talk. So my questions are in the similar vein, but I will still ask like if you have anything else to add. So one question I wanted to ask was, like in this quantum to classical transition, so I come from a field theory background, and for us we think of transitions in terms of phase transition, where you have an order parameter and there is some symmetry breaking, etc., like that. Do you expect something in this quantum to classical phase transition, like some kind of a phase transition description, some non-analyticity in order parameter?
I can do it. So this is now, you put your finger on the biggest problem in this collapse model stuff. They're not covariant, so there's not like a quantum field type formulation of it. And people have tried it many times. It has to do with what you do with the noise. So you get, in the typical noises which you use, you get correlation functions which have infinities, and then you would need to do like a cutoff. How do you do the cutoff? No one knows. So you try to come with physics and then motivate how you do cutoff, but it's a mess. So from a formal point of view, that is why most people, I guess, like yourself, coming from quantum field theory background, they don't like collapse models for exactly these reasons, because you don't have a relativistic formulation of these models. So I don't know. It will be, again, up to someone really smart to do it or to come up with an explanation. But it is one of the open points of collapse models to solve. Yeah? And then if you have this, you maybe can also look into more quantum field theory type effects which are predicted by this model. But that doesn't exist at the moment. Right?
I mean, can I say something to that? I have a mind.
Sure. Yeah.
So actually not for gravitational system, but we have worked on there are some magnetic system. So either it could be Heisenberg type or quantumizing type, where you sweep the field and you have a many-body entangled state. Okay, and then you sweep the field and above the critical points, there is a sudden collapse into the classical set where they are all disordered paramagnet, right? From a entangled state or like that. So but then there is no gravity there. It's purely quantum mechanics, and there is quantum field theory and all. So it's like quantum phase transition, but there is a sudden collapse at a particular field. So that would differentiate. Okay, so next is Kola.
Sorry, I just wanted to add to that. Yeah, 2 points. So your question is very good. As the system becomes more and more massive, is there a phase transition or a symmetry breaking? That's the kind of question you're asking, no?
Yeah.
In collapse models, that is not the case. I don't know whether that is the case in nature or not. That experiment will tell. But here, as I said to earlier question, you assume that for a single particle, superposition spontaneously collapses once in a very large time, capital T, and then it just scales with the number of particles in the system. Superposition lifetime becomes smaller and smaller, and for a chair it is maybe a microsecond or a nanosecond, but it's just scaling. There's no phase transition, at least in collapse models. Does that answer?
So maybe something like a crossover kind of thing.
It's a continuous process. See, if the superposition lifetime for a chair is a microsecond, the chair is still a spontaneously collapsing quantum system, but the lifetime is so short that we humans can't sense it. Maybe if there was a super being, that fellow would have, if he has a nanosecond level perception, he would see the chair in superpositions and say, oh, spontaneous collapse, quantum theory, etc. You see what I'm saying?
Yeah, I get it.
For me, that picture is good. Now, the second point, because Hendrik mentioned relativistic collapse models, or rather the absence of it. It's true, the collapse models are non-relativistic. I have a viewpoint on that. If you want to make relativistic collapse models, you have to treat space and time on the same footing. Here, in the non-relativistic theory, time is absolute. It's Newtonian time. Position is an operator, and there's a collapse in the position operator. If I want to make a relativistic collapse, and this is my view, not everybody would agree, that you have to raise time also to the status of an operator. Then you're already outside the domain of quantum field theory. Something else has to be a classical time parameter. The standard time t, x, y, z, that time in special relativity should become a time operator, just like the position operator, and there should be a spontaneous collapse in the time operator also. That's my picture. If you want to make relativistic collapse models, I don't know if we agree. Yeah. So this is what I call space-time collapse. Collapse of the wave function in operator space-time. So as I'll talk tomorrow, classical space-time comes from the collapse of operator space-time. But this is beyond special relativity and beyond quantum field theory. Okay.
In the interest of time, I won't ask any.
Right. So next is Kolahal.
Hello. So first of all, thank you to the speakers for these nice talks. My question is for Professor Hendrik. So you showed one slide on the Schrödinger-Newton equation, and immediately next to that there was a slide where the different time scales and the mass scales, they were plotted. So the question is, these time scales, do they represent the time scale for the measurement or the observation? And if that is so, then what is the rationale behind scanning those time scales? I mean, are we like experimentally scanning over all the time scales possible as we increase the mass? Or is there any guiding principles which tell me kind of, I mean, okay, we should, for this particular type of mass, we should look here or look there, something like that? That is a question.
Yeah, okay. Okay, so this is like for like the natural Schrödinger evolution, so there's no boost. It is basically just you have a certain mass system and you prepare an initial state and then you let it go in free evolution and then you basically observe or measure how it expands. And this Schrödinger-Newton equation predicts that there's a contraction, right? So you don't have a spread, it doesn't spread out, it basically contracts after some point. And now the question is, for a given mass, when does it happen? And the plot basically showed you know, how the mass-time correlation is. So for, 10 to the 8 atomic mass units, you have to wait 400 seconds before you would see that the contraction happens. That is like the effect you're after, right?
Okay, and I mean, if we go to the, say, low mass regime, let's say 1 AMU or even less than that, for example, electron mass is much less than that.
Then it would take much, much longer. Yeah.
Okay, thanks.
So, Arnab.
Hello, I'm Arnab Acharya from VNIT Nagpur. I enjoyed both of your talks very much. My question is, in the quantum to classical transition, the best theories we have are decoherence and these objective collapse models. But both of them suffer from a problem of basis. As in the objective collapse model, you have this arbitrary basis, localization basis. CSL has position, but there are models which have momentum and energy as the localization basis. In decoherence also, we have the problem of the preferred pointer basis. So my question is, in other words, the Hilbert space of quantum mechanics allows for infinite number of observables. But in classical world, we only find a very small set of observables. So how does this transition happen? And in your experiments in the mesoscopic domain, do you see any hints as in how this transition might happen?
I just share my thoughts. I mean, others may disagree, you may disagree. I think there's something very special about position in space and position in time. Space-time, make it relativistic. Space is that which is between classical objects, and time is that which is between classical events. So I am comfortable with the picture that, as Nicholas mentioned, detectors have positions, you see, and all measurements are eventually position measurements. Even if you are detecting spin, finally you check whether the pointer went to the left or to the right. I think there has to be a fundamental theory from beyond quantum theory from which we ought to derive collapse models. Then only I think we can answer your question about basis. I don't think there's a unambiguous answer to this.
Thank
Nicholas, you want to add something? Hendrik, there's something special about space-time, right?
Yeah.
Space-time and classical objects coexist. One is, you cannot talk of position of classical objects without space-time. You cannot talk of space-time without the position of classical objects. This background seems to be very essential for the current formulation of quantum theory. You need a background of space-time and classical objects to talk of quantum theory, Schrodinger evolution, and collapse. But this background clearly is a limiting case of quantum theory, right? Because classical objects are a limiting case of quantum theory. You cannot talk of space-time unless there are classical objects. This clearly points to that there has to be a way of understanding quantum theory, including its reductionist collapse aspect, without making any reference to detectors, space-time, measuring operators. We don't have that, we are trying. Did you see what I'm saying?
Yes, thank you so much. I have a follow-up question to Professor Ulbricht. So, your massive superpositions, are they helpful in some sort of quantum sensing applications?
Yeah, so that, of course, that's like, when we write grants, no one cares about foundations, so we have to say that's the best sensor ever. Yeah? So, and that's what we do. So, and actually, for instance, for the space experiment, there's, to be a bit more serious, there is like, I think, real scope for using these systems for instance, detecting gravity and gravity gradients. And that is, for instance, when you do what is called satellite geodesy. So you have a satellite which has a gravity sensor, and they're like missions like GRACE and GOGI, and they did like a mapping of the mass distribution on Earth, which is very interesting and very important for geology and also for weather and climate change and these kind of things. You can monitor how ice caps are melting and like water levels are rising, and you can detect how this, like the water in the underground, how's like the water table changing there. So that is like serious problems which I think can be helped with these kind of sensors. So one big advantage is that, if we talk about this levitated nanoparticle platform, it's very compact compared to others. So you can, as we have hopefully demonstrate in like half a year, you can put them on a satellite and you can operate them. And they're still very sensitive, so you have a very high acceleration sensitivity. Now, if you have this, you have basically one point where you can measure gravity on Earth. Now, because it's so small and compact, you can actually have many of those satellites at the same time, and they operate as a network. So you can, by that, increase the spatial and temporal resolution. So you can map many locations with a higher resolution more often. And, there's like a lot of things people have to still invent this off. No, you also want to say? Yeah. So that's just one, and Peter has many more.
Thank you.
So yeah, so I mean, beyond sort of practical commercial possibilities, we're currently using these sensors for dark matter, as I mentioned. And so, there's a sort of if you can get to the standard quantum limit in these systems, then you can make sensitive measurements of momentum transfer. But also, if you can create a superposition, then it's very sensitive to, extremely sensitive to a whole range of dark matter models, but also known things like a whole range of particles, for example, neutrons, the sort of background neutron fog that exists that people are interested in measuring. So, beyond applications, you can also look at other areas of fundamental physics with these sensors.
Thank you so much.
Thanks, sir.
Yeah.
So next is Saurabh Sahu.
Thank you very much for this talks. So my question is, when we can actually say that the system made a transition from quantum to classical, like whether it is by the absence of the phase relations between different eigenstates, or when in the absence of superposition, and what exactly is a classical result when you are talking about the transition? Like the wave function collapse is, according to me, it describes one particular aspect which is still quantum. We are getting one of the outcomes which is predicted by quantum mechanics. So, and the classical trajectories associated with the unphased theorem, or they are the classical results. So this is my first question.
I guess, in one of the topics that I covered, I mean, basically the measurement there was, looking at the sort of decoherence time, essentially. So looking at essentially, when the negativity of the Wigner function is no longer the case. So I think that's a fairly sort of concrete way of doing things, if that's available.
Yeah, so I think it's a very good question. I don't have a deep answer. Just, a pragmatic experimentalist answer is when I do an interferometry experiment, I observe an interference pattern with a certain visibility. And that visibility is basically my parameter which I probe. And then I, run my experiment at different conditions. I maybe increase the mass of my particle, or I, extend the length of the interferometer, or I let it interact with, gas particles which I put into the vacuum chamber, or I send some photons, and I basically study how this visibility is changing depending on those parameters. So that is my experimental parameter.
But with a reduced visibility or the absence of the interference pattern, still superposition is there, right? So can we call it like it did a transition?
I mean, okay, so I would say, okay, if I see an interference pattern, it means there's like a superposition, yeah? So in a kind of very, very naive picture, I have this probability to go through two slits of the grating in a way. And if I don't see visibility, then this doesn't happen anymore. So I have like a probability that the majority goes only through one slit, and then I see a different pattern. So that would be my very pragmatic take on it.
Okay, so thanks.
My next question,
I
one
think
more small,
can we
very
come
small
back
question.
to it later after everybody has asked. Okay. You already had 2 questions, so let's stick to it. So next is Sagnik Ray.
So my question actually relates to the CSL model. I'm not sure if I'm right, but it seems like if we have a white noise background, then that might lead to non-conservation of energy of isolated systems, one. And the second part is, this model doesn't explain the origin of the white noise. So for that, we have to look into other physical phenomena. Now, given that most of the physical phenomena now, with more exotic phenomena, can be explained via quantum mechanical effects, and we are saying white noise might be arising from that part, doesn't it make the logic circular? So that's my question.
Yeah, so your point is very good. Was it a first question before the white noise? The heating, yes, the non-conservation of energy. You are right. There has to be a reservoir from which the system is extracting energy. If we believe in energy conservation, which I think we should, then this system is heating up because it is interacting with the noise field. The classical motion will have a jiggle, what Hendrik called non-interferometric test of collapse model, the test of heating. So if it's heating up, it's gaining kinetic energy, and that has to come from somewhere. So we assume that there's a background noise field and the total energy is conserved. Now your other point is really good, that the background noise field should obey quantum field theory, and now you are going round and round, circular. So my answer to that is I don't know that the background field obeys quantum theory. There has to be an underlying theory from which in various limits you can derive, should be able to derive Schrodinger evolution, CSL model, as well as the noise field. A good underlying theory would account for all of this. Only that would tell us what are the equations of motion for the noise field. So I'll touch upon that a little bit tomorrow. I mean, part of my talk attempts to answer what is the possible theory underlying collapse model. These are phenomenological. We have proposed a very interesting modification of the Schrodinger equation so as to be able to explain collapse in a experimentally falsifiable way. The prediction is falsifiable, yeah? It has these parameters, gamma, RC, which is what Hendrik showed, the exclusion plot. But we would definitely like an underlying theory, which will not be quantum theory, because it has to be something more general, and that theory should predict, should derive all this, yeah?
Thank you, sir.
What about physical mechanism? What do you think?
What is going on in collapse? Okay, so I give you my picture, just with the analogy. Let's assume for the moment, may not be correct, that the background noise field is the same as what we call dark energy. And you can sort of argue from these so-called holographic grounds that the dark energy has 10 to the power 120 degrees of freedom. Visible matter, from which everything is made, has around 10 to the power 80 degrees of freedom. And the 10 to the 80 protons or electrons in the universe. Now you compare these numbers. 10 to the 120, that's the true universe. 10 to the 80 is the apparent universe without dark energy. So my picture is that every once in a while, a nucleon from this 10 to the 80 goes and hits one of those 10 to the 120, and maybe that's what's causing collapse. So since you asked, I give you my picture. It may be wrong, but we need a picture. We need a picture. Yeah.
Okay, so next is Neelaj Saha.
Yeah. So, hi, first of all, thank you for your talk. It was really interesting. I'm a final year MS student at IISER Mohali, and I'm deeply intrigued by topics of quantum aspects in quantum aspects of gravity and how to probe them. So I'll kind of go back to that. So in your slides, you showed two very recent tests where one of them is a spin entanglement-based test, where we can show that gravitational interaction indeed entangles masses, and we can show that that entanglement is obviously a quantum effect, so gravity mediates through, has a quantum effect in it. And the second test, if I'm not wrong, it has to do with measurement-induced disturbance. So you make a measurement and that disturbs, and if that disturbance is irreducible, it's again, irreducible disturbance is a quantum entity. So can you elaborate a bit more on the distinction between these two types of things? Because the second test also relies on entanglement. There is entanglement developed between the probe and the source masses, right? So how is the second test distinct from the first one?
I don't know. I mean, if you, I think, work out the equations, you find that actually the first interesting thing is that both should happen in a similar regime, and that has simply to do with the scaling of gravity. So the effect basically starts to show up in the entanglement system and also in the superposition system. And then I think from the point of what kind of statement or what would we learn about gravity from these experiments, I think both are equal in a way, right? So that it is not that you could say, now we fully understand what gravity is and that there is quantum gravity or not. But you get like a first hint where it could go. So it would be the first experiment ever which probes into, quantum aspects of gravity. I think that's the claim people are making here. So now then the question is, what is like the easier experiment, right? Is it easier to generate one superposition and probe how the gravity looks like? How, that is what your second example, you called it, you take a measurement and then you infer basically how, space-time or gravity looked like of that superposition state. Is that easier than having two particles and you put each in a superposition and then try to entangle them? So my thinking is that the first one, so to have just a single particle which you put in a superposition and then probe the superposition, is simpler because it's only one system. But that is like a very naive argument. So it could be that for some evolved reasons, it is much easier to work with entanglement. Yeah? So that there are some indications that in photonic experiments that is very successful. So maybe also in these large mass systems, entanglement turns out to be like an easier or sooner to reach milestone for this experiment. But at this point, I don't know. You see, we have still 10 orders of magnitude to go. Yeah? We're learning how to do these experiments at the moment, and I think to give you like an estimate of a timescale, I think a serious attempt on doing one of these experiments is maybe in a decade, right? So we have to really build the technology and learn more about these systems and how we can use them. But there are many options, and people are really interested, and many people working on it, but we are still at the beginning. We have to be very clear about this, right? That we don't promise too much. Yeah.
Right. Can I ask a very quick follow-up? So in the second sort of experiment where we use measurement-induced disturbance, if I'm am I wrong in thinking this, that disturbance can also be caused by the probe and the source interaction? How can we conclusively say that the disturbance is indeed induced by measurement and not by something else? So the NDC violation that has been worked out in the paper, how is it exclusively because of the measurement and not maybe just the interaction between the probe and the source?
Yeah, no, you're right. That is like the biggest challenge, and I have no good answer. So, one would need to look at this in much more detail, yes. Yeah.
I understand. Thanks a lot.
Right. So next is Arun K. Das.
Thank you, professors, for such illuminating talks. So my question is, Leggettgard inequality is a guiding principle that ensures the quantumness of macroscopic systems. So in your talk. So what is the guiding principle that will ensure the quantumness of macroscopic system? I think you may have mentioned, but I have not understood.
Sure. Yeah, Leggett-Garg, I didn't mention it too much, but it's actually a lot of work we do with Dipankar Home and also Sugato Bose on this one, and try to come up with measurement-based schemes of these harmonic oscillator systems and probe them in a specific way, and using all the tricks in the book on measurements to infer and to basically probe a Leggett-Garg type inequality for the dynamics of the system. So you look for correlations in time. Yeah. I don't know exactly what you mean by guiding principle. So if I do like if I think about interferometry experiment or also non-interferometric experiments, I have basically a guiding prediction from standard quantum mechanics, which if it's in a pure form, it basically makes a statement you can always, do quantum states. There is no limit. There is no fundamental limit. It's just your capability as an experimentalist to isolate your system, and then it should always happen. Yeah. And so that is like the expectation. Then there are these other models which clearly say, no, there's like a fundamental limit. There's like a threshold which, you cannot do nothing, and you will not be able to see any kind of quantumness beyond. So I don't know if that answers the question.
Yeah, guiding principle means like what kind of inequality or what kind of equation that you have checked, whether it is violated by your system.
Yes, this equation will be violated by macroscopic systems if quantum mechanics is right and his collapse models are wrong. I mean, to put it in simple words, if I send a tennis ball through a double slit experiment, it should show interference. If you send a succession of tennis balls, that's what this theory, this equation is saying. Tennis balls will not show double slit interference. Quantum mechanics is saying tennis balls will show double slit interference. So there's a clear test, yeah?
I think in like more direct words, what you test is the quantum superposition principle, right? So that is your guiding principle, I guess. And you see if that basically fails or if that is universal. That's the thing, yeah.
Another follow-up question is there any sharp boundary between classical and quantum regime? Like you have defined a macroscopicity for the degree of macroscopicness. So what is the threshold value of that macroscopicity above which you will call it is macroscopic, it is classical, and below this it is quantum?
Okay. So that's phenomenological. So all is very ad hoc. So in the same way you assume that like on the basis of nuclei you count particles. Also in the very first collapse model, which is GRW, Girardi, Rimini, Weber from '86, I think. They basically did, it's really out of the blue. They just say, okay, if I have an object and I can see it with the naked eye and I can see it's localized, then that is classical. That's what they define it. That is 1 micrometer, and that is what gives the bound of the GRW model. That is what they define as the threshold. So everything which is smaller is, allowed to be quantum mechanically, so you expect superpositions there. And everything which is larger than that is, not able to be in a superposition state, right? So the superposition principle is violated. But that is completely ad hoc again, yeah? So you could come up with a different idea. So Stephen Adler had 2 different other models. These were also on the map, where he used basically different ad hoc principles to define what he thinks where this boundary should be, right? But I guess it's still anyone's guess. Yeah.
According to collapse models, we should redefine what we mean by classical. Strictly, there are no classical systems. What we call classical is a quantum system in which the superposition lifetime is so short that an experimentalist today is not able to detect it. Yeah? So I want to remove the distinction between quantum and classical. Classical systems are short-lived quantum systems. Yeah, you can say that, yeah. I think it also answers your question. Right, yeah, I wanted to say that, yes.
Oh, thank you very much.
Ramanandan? Hey, Tejinder, Ramnandan.
Myself, Ramnandan, from Aizawl, Kolkata. I have a just very short question. As we know that we can replace gravity with accelerating frame of reference. So, can an accelerating frame of reference mimic the effect of a source mass, measuring the quantum gravity or this quantum entanglement based on Einstein equivalence principle?
Yeah, very good question. I think yes, to some extent. There are lots of caveats, but in principle, yes. And they're very interesting things. So it, also, when you think about quantum field theory, that links to Unruh effect and these kind of things. So very, very interesting stuff. And then the question is, what is the acceleration? And there's a fundamental difference between rotation and linear acceleration. So for instance, Unruh effect, strictly you only have for linear acceleration, but not for rotation. You don't build up velocity, so that, you can explain this very nicely. So again, so that the difference in what you expect and how you do the acceleration, but I think you can have, assuming that the equivalence principle, so like the foundation of GR is there, so that is, I guess, the basic assumption you do, then you can use it to mimic effects which you also have in gravity. So some people may call this an analog system, which I think would be fair, because you're technically not dealing directly with gravity, you're not necessarily dealing with a large mass, but you could study the similar type of dynamics in a system which has the right type of acceleration. And I like this a lot. So I think it's a very rich dynamics, and you have many, as an experimentalist, I always find it fascinating if you start with an idea, and I think you always should start with the fundamental question, and then the next question is, in what kind of system can you see it? Can you study it? Can you explore it? And if you can basically broaden the basis of those systems, if you can now do an experiment in a system which initially looked like as completely the wrong system, so you want to study gravity, but you learn you can do it in a photonic system, that's amazing, yeah? Because you can use strong advantages of photonic systems and learn something about physics where you not expected it. So these links I like a lot, and I think acceleration is a good pointer to make this bridge. Yeah? So there are also some papers which I have published on this.
It's just a quick question to what he mentioned. You had mentioned about 1 micrometer as the range where macroscopic would be defined. That's for the length. Is it true also for the mass scale?
Yeah, so I mean, this is like, you assume like a typical mass density, and then this is, if you have a 1 micrometer particle, then it is like, I don't know, a little metal ball, or it could be even glass, so then it's like maybe a factor of 2, 3 difference, but it doesn't matter too much. So it is basically a statement about the mass.
Okay, no, because in Parker's talk, he mentioned about 10 to the power minus 24 kgs as the mass that is taken for defining macroscopicity. So that's the reason I just asked.
Yes, yeah, you can map this into.
That's the molecular system.
So molecular system, yeah. Thank you.
Yeah, so I mean, to give you, if you do like strictly interferometric experiment, to reach the this GRW value of 1 micrometer size, that would be, I think, 10 to the minus 14 kilograms. And at the moment they're at, so 1 million atomic mass units, so that's 10 to the minus 21 kilograms. So you still have 6, 7 orders of magnitude to go. Yeah.
Right. So as we were following the norm is that allowing younger people to ask the questions first. We have sort of exhausted the younger people with the time remaining. Now not so younger people first, and then a little more not so younger people. There are only 2 people. So first, so there are 2 people remaining who have given the choices here, Kulkarni. So that's what I am respecting. So Manavendra, and followed by concluding remarks by Professor Home, and then if you have any questions, we can go into the lunch and this thing. And now at this moment, I will take your leave. So Professor Banerjee will conduct that.
Okay, so thank you for the discussions. I have 1 comment and 1 question, and I place both of them now. So what I understood from the discussion of, let's say, the neutron star or BEC, Bose-Einstein condensate, it turns out that if I want to see some object to collapse faster, that means it has to have much more degree of genuine entanglement. So it's kind of counterintuitive, no? More quantum behavior it may show, looks like more classical it will look like, isn't it? This is like the comment if I understood it correctly. Okay, so, and the question is here, is that I know that most of the object we are talking about obviously interact with the electromagnetic field much more stronger or with much more coupling strength than the gravitational field. So what motivates you to come up with a model that exclusively rely on gravitational field induced collapse? Why not, let's say, stochastic electromagnetic field? Why not? And these are there in abundance.
I think, that is the challenge, right? Is that all of those things are stronger. Casimir interactions, are probably, then there's Coulomb interactions, and then, So I think that is the challenge and the gravitational interaction is so much weaker. So that's where the challenge in these experiments is to have shielding to protect from Casimir interactions, and we have to check charge distribution and all of those sorts of things. So you're absolutely right, I think.
Yes, and for your comment, so correlation, right? So the important part is like the correlation part is not necessarily entanglement, not necessarily quantum correlation, which of course we know from Harald's and Nicola's work is the strongest correlation you find. So when you measure one system, the other one is in exactly the same state all the time. So that is like, the strongest correlation you know, but that is not what you need in collapse models. What it wants to say is that you not have individual particles. If you think of atoms, you can have two cases. So you have a BEC, a Bose-Einstein condensate of atoms, and actually there you have, even though it is described by a single particle wave function in a specific state, you have weakly interacting atoms. So each atom is individual and does not even know that the others are there. So if you would do like a decoherence experiment, so you would have like a local interaction, it would basically kick out one atom, but the rest of the condensate wouldn't even care, right? And that's a system which is not fit for testing collapse models because it doesn't scale with the number of atoms. If you have on the other side something like a nanoparticle where you have likely the same number of atoms, but they're now chemically bound, right? So that would be a classical correlation. So if you affect one by a hit, then all the others know it and they shake and they move. So you really have a center of mass motion which contains n number of atoms. And this is now a system which scales in the sense of collapse models, because if you do the same decoherence experiment again and you kick one atom, the whole big particle goes, all the other atoms also go. That is your cat state, yeah? That's your Schrödinger cat state.
So what you wanted to say is that when I define macroscopicity, it is not only the mass or the size, rather the degree of interaction, and so let's say the degree of entanglement or correlation has to be taken care of.
Yeah, so that is in a way also there, and it's not explicitly mentioned as a criterion, but it's an important one.
Okay.
Yeah.
And just to come back to, I think with this I will finish also. So it seems like, so this general kind of narrative is coming like that, well, gravitational field is responsible for decoherence or collapse. It is not really the case. It is essentially an experimentally viable approach to check whether a background stochastic field can induce collapse. Mm-hmm. Is that right?
Yeah.
Okay, thank you.
Professor Dipankar Home.
First of all, I thank the speakers and also the so many students and others who asked very interesting questions. But I will just make two brief points and one short question to Peter, which maybe answer may be interesting to the students. So first, the short question to Peter. Schwinger in around 1987-88 had suggested that Stern-Gerlach, like we talked about other, but Stern-Gerlach is also an interferometric test. And Stern-Gerlach, he had proposed that testing quantumness by whether one can recombine the spatially separated beams in Stern-Gerlach by reversing the magnetic field. That would be a critical test of unitarity of quantum mechanics. Yes. By the way, I think my personal view is that any discussion of quantum classical must begin by clearly stating what we mean by quantumness. So I would define quantumness by, of course, superposition principle, but also an aspect that it is unitarity is also considered part of quantumness. And another very important ingredient which has been overlooked is that measurement on any quantum system must necessarily must have an irreducible disturbance. That does not mean collapse, but disturbance means modifying the system property, because that just generating the entanglement between the probe and the system can itself affect the property of the probe, of the source, which is interacting with the probe. In fact, this is what is used in that second proposal for the gravity test. So my question is, so what is, with the modern technology development of Stern-Gerlach, and Schwinger did the analysis and showed that an incredible infinite precision in reversing the magnetic field. So how much we have traversed after 1987? If on atoms, I understand people have done, but have the recombination so that, and that is critical also for this gravity experiment.
So as you say, I mean, actually it's only recently been done with atomic systems, right? So this recombination has been done by Ron Fullman using cold atoms basically. But you know, the challenge then will be in these systems how you go about that, because it does require incredible precision. Well, I mean, I'm not an expert in that, but the general feeling is that this, I mean, the same procedure that you use with cold atoms can be applied in these much larger systems, these much larger Ramsey experiments. So, I mean, it's not a very good, but it certainly hasn't been done yet. And I think it, you know, as Hendrik said, it's a long way off, but I think it's a feasible thing to do and something that we need to do.
Yeah, maybe to add this, also historically that's very interesting, because there was a big discussion if actually Stern-Gerlach, the original experiment, if that basically showed anything quantum or not, right? And we don't know because they didn't recombine, right? So it could be you get at the point, so you split basically in the magnets, and you have basically the two measurement points, and what you know from there is that just one is spin up and the other is spin down. But you don't know if the initial state was actually a coherent superposition or just a statistical mixture. So because you have to do it many times, it could be that in one case it was this spin, in the other case it was this spin, but it was never a superposition. And that you only get if you do the recombination and you actually get like the real interference pattern, if you want, in your result. Yeah? And that is what Ron did, and he showed it. And so the critical point, that there are two things which you need now to map to these larger mass systems when you want to do it with an V center in diamond for a nanoparticle. You need to be able to prepare this initial superposition state, and that they can do by magnetic resonance techniques, so they can generate this initial superposition of the spin, and then there's a magnetic field gradient which is mapping this to the center of mass motion, and then you have it. The second thing you have to do is that the boost operation, which is like your Stern-Gerlach beam splitter, so that is like the magnetic field which is spatially separating the two spin states, that has to be a fully coherent operation. So that has to preserve the initial coherent state to the point where you recombine it. And I think that is like a more difficult part, and that has not been demonstrated by anyone for these large mass systems, right? So it's likely, has to be very fast, and you have also like a limited spin coherent time, so the T1 or T2 time of the electron spin is very, very short, so that means you have to open and close the interferometer within that, spin coherence time. And then, of course, you have also the center of mass motion coherence, which, depends on background gas collisions and temperature by a blackbody radiation, and all of these things that count in. So I think that is like the challenging part, to preserve coherence while you basically close the interferometer. Yeah.
Okay, thanks.
But, I guess it's not the only way either. I mean, in order to do these gravitational entanglement experiments, I mean, there are other interferometric methods. So even if it doesn't work, there are other methods.
And just one short comment, because Leggett-Kirk inequality was mentioned in the comments, and that it also tests superposition. But there is one fundamental difference with the other tests and Leggett-Kirk type test. Leggett-Kirk is a Bell-type inequality, temporal version, based on just fundamental assumptions about how systems should behave, means quantum or classical or not. That is about non-invasivity of measurements. No, measurements has to be invasive nature. So Leggett-Kirk can be looked upon as a measure of the invasive nature of measurements consequence. In that sense, Leggett-Kirk or this no disturbance condition measurement, which is the second proposal for the gravity, they in a sense complements the other type of studies, which are also testing superposition, but this is more theory independent, like Bell inequality test is. This Bell inequality tests quantumness, but in a more device independent way, as they say. They get Gark's similar type of device independent test of non-classical.
If there is any further question, then one can.
This is about just to know one information, because recently, at least in news, it appeared that people can create or realize Schrodinger cat state with tardigrades, the water bear.
With what? Sorry.
Water bear, tardigrades, sorry.
Oh, yeah.
Yeah. So because it's really macroscopic, not only that, it's some living organism in that sense. So can you say something about it?
I can't remember the details, but I don't think it's quite true. The
tardigrades are organisms.
Yeah,
organisms.
It's about 10 to the minus 12, I think, kilograms. It's quite a large thing.
I don't know this. I don't know this specific experiment, but you have to. Of course, there's classical interference, and you can have, an interference pattern in any kind of wave setting, right? So, what is like the difference for a quantum experiment? That is, if you do it with, a single quantum entity, and you actually not interfere like two different partial waves, but you start from, it's maybe not the nicest word to explain it. I would need to think about it a bit more, but just ad hoc, you need like a single particle where you have, the superposition of this probability to be in different locations, yeah? And then you recombine, and then you see an interference pattern. But you have just one particle. That's like the key thing. That's what makes it quantum. And I would highly, highly doubt that this is really realized in this experiment. I have no worry on, no issue in saying that it's a nice interference experiment and you can see it, but it's a classical interference experiment. These are waves, right?
So they say that because it can go below something 3 Kelvin and so, and they still can survive, this organism. And they're kind of saying that it's between dead and alive state you can create, and some kind of quantum nature they can see.
Again,
but anyway.
I don't know the details of the experiment. One would need to have a look, but I wouldn't be surprised if that is, not the proper quantum superposition.
Okay.
Yeah, just a remark on what you said earlier, that high degree of entanglement leading to classicality is counterintuitive, because entanglement is a quantum property. What collapse models are saying, that high degree of entanglement makes the superposition lifetime very short, which is what is responsible for. So this is a difference from quantum theory. In quantum theory, irrespective of how large is the entanglement, the superposition lifetime will be infinite. But collapse model is saying no. You increase the amount of entanglement, you decrease the superposition lifetime. And that is consistent with what we see. So I would say it's intuitive, not counterintuitive.
Yes, just one more question here.
Yeah, I just have a quick follow-up question to what Professor T.P. Singh was saying about the neutron star, that these macroscopic quantum systems are essentially comprising of separable wave functions for the particles, and that's why the scaling for the CSL models doesn't happen quite the same way. So I was wondering, doesn't the exchange statistics, I mean, given the fact that the wave function has to be antisymmetric under an exchange, doesn't that make it highly entangled for the neutron star?
To my understanding, no. Entanglement means you take the state which is, let's say, obeying exchange statistics, use that to create entanglement. It's like your BC here and BC here.
Okay.
Each state by itself is symmetric under particle exchange, this one also. But you now try to create a superposition of these two after entangling a large number. So exchange statistics is a property of the state. But in addition, you want to create entanglement of 2 copies of the symmetric state, right?
I see.
Isn't it?
I see. Yeah, no, I was just wondering how does the entanglement feature in this equation, because all it says here is just the mass
that's a good point. This gamma amplifies with mass or number of particles.
Exactly, yeah.
But the state psi, it's important, you see, the state psi is a state of the full system.
Right.
If the state is a product state, that won't do, because I think for a product state this will factorize.
I see, okay.
You need an entangled state. He's saying, why don't we specify this explicitly, but I don't have an answer for that. Yeah, it's in there. So see your gamma. If your state is a product state, your gamma is going to be just the number for a single particle.
I see.
It won't be n times for a single. I think that's the answer. Right.
I see.
You have to give a prescription for how gamma scales with mass.
Right. Okay. Thank you.
Okay, we now have to bring this session, extremely interesting session, to an end. All good things end sometime or other. This one also has to. So now it is time for lunch, and we will again assemble at 2:30. So take lunch fast. Yeah, a few announcements here.
So those who have not registered yet or have not collected their T-shirt for which they have already paid can do that from the registration counter today. Okay. So sometimes somebody will sit during the lunch hour. So in case you still haven't registered or still haven't gotten the T-shirt you have booked,